Fine. Now we can continue with our discussion. We said that we have these properties of an optimum Lloyd quantizer. And these properties, we can show a few of them. For example, I may start with the first one. And in fact, what I will show as the first property is not really yi is equal to this, which is equal to this, but I will start by saying that yi is already equal to this one. It must be. But the definition of this one could be written like this, which is very mathematical way of putting things. So I will show that, sorry, this is equal to this, but I will show it by showing that this is equal to this, the same thing. So proof of, that's so ugly, sorry, proof of 1. So what was the expression? The expression I will copy from here is S with an SI x times fx of x dx divided by, within the same region, SI fx of x dx. So what is this equal to? How can I write this? And the way to write it down is to keep the numerator first, but the denominator essentially corresponds to the probability of x, the input, being inside the region SI, because there are different regions. So what is the probability that it fits inside SI will be determined by this integral of the probability density function, which will give you a fraction of the whole probability density function, which integrates to 1. So this will be less than 1. So the denominator I will quite simply write as probability of x being inside SI, essentially. And then I can erase this. Let's not be lazy and let me write it in a separate step. We can write it like inside SI. I will write it as x fx of x divided by this probability of x inside SI dx. So reform it inside the integration. And then I can see this part, fx of x, the probability density function, divided by the probability of x inside SI, is essentially the definition of fx of x such that x is inside SI. So it's a conditional PDF definition that we come up with inside this fraction. And therefore, we can write this to be equal to SI x times fx of x, condition that it is inside SI dx, which is naturally this time the definition of expected value of x such that x is inside SI. So as you see, originally you could also say that this is of course the definition that the definition of expected value of x, condition that x is inside SI. Why did I do these steps? It's some gimmick, as you see, to come up with the expression. So I have shown that this is equal to this, which is already equal to yi. Okay. So quite a meaningless way of putting things, but that's what it is. And in data processing, we will see that it will be different. These are just analytical results that we think about, which gives us some insight about what to expect. For example, the proof of the second one, which is which was the expected value of quantization error is equal to 0. So this will be a little bit more meaningful, not as nonsense as the proof that I have given you for part 1. This is a little bit more meaningful. So we are going to see that the expected value of quantization error epsilon is essentially equal to 0. Is it? Let's see it. First of all, the expected value is obtained by an integral which gives us the expected value. So what's the parameter that we are integrating? It is epsilon. And what is the probability density function? It's the conditional probability density function of x, like this. All right. So this thing is supposed to be evaluated for the expected value expression, which we claim to be 0. And that is equal to x minus yi optimum, I will say, the optimized decoder output. That x minus yi optimum is epsilon. That is the definition of epsilon, by the way, that I have been using, times the conditional PDF, like this. And then I can split this expression into x times this minus y times this format. Okay, just the distribution property of a linear integral operator. So it will become x times fx, x condition that it's inside Si dx, minus yi optimum integral. Originally, yi optimum was inside the integral, but since it's constant, it has nothing to do with x, the integration parameter of x. It can be taken out of the integral. That's what I did. And inside the integral, I'm only left with the conditional PDF. And at this point, we make a few observations. First of all, this thing is the very definition of yi. It is the expected value of x, condition that x is inside Si, which was this. Excuse me. This. Okay. By the way, you don't have to use Si here. This could be replaced with a range of -infinity to infinity, because the range is already embedded or incorporated into the conditional PDF here. So this thing overall is essentially the definition of yi optimum. And this is the integral of a marginal probability density function or a conditional probability density function, which is a probability density function. And when you integrate from -infinity to infinity, it gives you 1. So what do we have? We have yi optimum minus yi optimum times 1, which is equal to 0. Okay, that was what we have been trying to prove. So this is the way. Then you see that the third property, which is just a generalization of all the cases, this is one case where it is inside Si. If it is valid for all Si, for all regions or for all outputs of quantization, it's equal to 0, then it is overall expected value should be equal to 0. Why didn't I write it? It's equal to 0. So the proof of third, which is left to you, then will be a piece of cake by knowing that it's 0 for each individual case. And then I will continue with the fourth one, this one, which is fine. It's not trivial either. It's something like the proof of the second one. It's a little bit more meaningful. Let me also do that. But the rest will be left to you, probably, as a take-home exam question. I may or may not ask. Sometimes just feel lazy about it and don't ask, but whatever. Let us prove the fourth one. The claim is that the expected value of yi optimum times the quantization error is equal to 0. But what is it? I will use a trick which is somehow similar to the one that I used for proving the second part, which was expectation of yi optimum times x minus yi optimum kind of thing. Okay, because epsilon is x minus yi optimum. So we will proceed from there, and the definition of that in the form of an integral is from minus infinity to infinity yi x minus yi. I'm not putting opt in the subscript because we know that these are the optimal. To keep it a little bit short, let's do it like this. Fx x condition that x is inside Si. Okay, this is the thing that I'm trying to integrate. I will be integrating, and again I will split it into two parts. One part will be related to yi times x times the conditional PDF dx integration. The other one is my yi times yi, which is yi squared with a minus sign times the conditional PDF integrated. So I'm splitting the integral using the distribution property of a linear operator of integral. And that will give me yi to be outside of the integral because it has no x inside. So it's a term unrelated to the integration variable. But inside the integration variable, I have x times fx x condition that it's inside Si dx for the first part minus this minus sign yi times yi, which is yi square out of the integral again because it has nothing related to x. The integral fx x condition that it's inside Si. So in general, this integral can be split into this form. And here again, we have some observations that this one is equal to yi. And this one is the integral of the PDF, which gives you 1. So what do we have? Here we have yi times yi, which is yi squared, minus yi squared times 1. And what is that? It's equal to 0. So that's how we can literally prove the fourth property, telling me that the optimum quantizer output yi is orthogonal to the quantization error because the multiplication expected value will give you a 0. The others, as I say, they are up to you. Now, we can therefore, using these properties and all the other things, we boil down everything into two Lloyd iteration entities. In the case of squared error, or the distance that we are using between two signals as the square distance, if we are using like this, we will have xi to be optimized to be equal to the halfway between yi optimum and let's say yi minus 1 optimum. It depends on which one you start to choose as yi. To the left is the boundary or to the left is the output. It depends on your definitions or programming, if you wish, if you're making a programming. That is the first, and the second iteration is telling me that yi optimal is equal to the center of mass of the region, which is Si f x times fx of x dx divided by inside Si again fx x dx, which is the formula for the centroid. Now that Si is determined, or they are bounded between xi and xi plus 1, we could also write it in more explicitly like this. It's between xi optimum to xi plus 1 optimum of x fx of x dx divided by, again, xi optimum from xi optimum to xi plus 1 optimum fx of x dx. So as you see in the first expression, I'm using yi, set of yi or yi minus 1, yi plus 1, etc. This set to find xi's, and here I'm using those xi's as the regions, as the boundaries of these integrals to evaluate the centroid and determine yi. And we iterate between these. We do one and then continue with the other one. Therefore, it requires, since it's an iteration, it requires an initial condition. It requires its starting point. And a smart starting point, which is something that I can recommend technically, is to observe the dynamic range of the values first, and then start from a uniform quantization and see how this iteration, Lloyd iteration, converges. If you see that the probability density function is focused or condensed to some region, it may be wise to start by first narrowly splitting those points and then sparsely splitting the less frequent regions. Start from that kind of a place, which is automatically something close to the correct solution, correct optimum solution. You start from there, and the Lloyd iteration will give you a fine-tuning of that, and it will find eventually the correct result. Now, at this point, I will end the lecture with one example, which is a numerical example. And since it's a numerical example, you will see that things are actually, using numbers, using data, things are actually easier than this one. For example, this is telling me to find the centroid, but what is the centroid? We don't even have a probability density function or anything. We just have data. From that data, what you can do to approximate the probability density function from the data is to use histograms. For example, you can draw the histogram of the data within bins of intervals, and you have some curve maybe. But anyway, using data, actually the Lloyd max iteration is simpler. We don't, we do this part is the same. If you have the data, if you have the output values, then the boundary is just the midway. But the centroid definition is not like this anymore. We will quite simply find the average of the data within the region of SI. We just sum them up and divide by the number. It will be an average value. We will use that average value for the representation. And that's it. And let's do it then. Let's do a data example. So we have the data. And the data is consisting of numbers like this. It's minus 0.9. Of course, I will have some few data. Minus 0.8 and minus 0.7, minus 0.6, minus 0.2, minus 0.2, 0.1, 0.1, then 0.7 and 0.7 and 1.0. And I will design a 3-level quantizer because things look like containing 3 clusters, as we see. Probably the first cluster will be somewhere here, the second cluster will be somewhere here, the third cluster will be somewhere here on their centroids. I can visually see this. If I want to make a quantizer, the first quantizer output will be like minus 0.75 for this. It will be somewhere around 0 here, and it will be somewhere around 0.8 for this cluster. So 3-level quantizer is almost there. But of course, if you have a lot of data, things won't be as easy as this case, and you have to run the algorithm. And since we are going to run it with our pencil and paper, it must be easy like this one. So let's now start. And as a start, the yi set I will choose in step 1. It's an initial condition. It will be -1, 0, and 1. I will start from there because it looks logical according to the data. So since yi's are here, then I will first have to classify each of the data that I have here into classes that are represented by -1, 0, and 1. According to what? According to the nearest neighbor relation. For example, if I take minus 0.9, it will belong to the set which is represented by -1 because it's nearest to this. This minus 0.8 will also belong to the same class. Minus 0.7 will belong to this class. Minus 0.6 will also belong to this class, luckily. And so let me write it like this. The first set I will call S0 is represented by minus 0.9, minus 0.8, minus 0.7, and minus 0.6. The other set S1 will be the ones with value minus 0.2 and 0.1, which will be nearest to, so these will be nearest to -1. The other 4 will be nearest to the value 0, minus 0.2, minus 0.2, 0.1, and 0.1 will belong to the class which is represented by 0. And the final class will contain 0.7, 0.7, and 1.0, which is nearest to the class represented by 1. But at this point, I have to, so I didn't choose the boundaries. I didn't draw the boundaries, but I found the classes. In fact, it's more reasonable to draw it like that. We don't really need to draw the boundaries. The boundaries are clearly the halfway between 0 and 1, and 1 and sorry, -1 and 0, and 0 and 1. So essentially, x0 is minus infinity, by the way. X1 is minus 0.5, which is minus 1 plus 0 over 2. X2 is 0.5, which is 0 plus 1 over 2. And X3 is actually, again, infinity. So these are my regions. From minus infinity to minus 0.5 is one region, and these belong to that region. You can think of it like that. Or this range is between minus 0.5 and plus 0.5. So these belong to the second set. But we don't really use these terms, x0, x1, x2, and x3, while making clusters. We just measure according to the nearest neighbor, that's it. So making this class assignments does not really need the knowledge of the boundaries as minus 0.5 or 0.5. They are obvious. You just do nearest neighbor assignments. And then at step 2, you do something else. Since we make these clusters of S0, S1, and S2, now we have to find the centroids of those clusters. So what is, for example, Y0 for S0? And that is equal to S0 is this set, as you see, and the representation value, the output is just the average, like the conditional expectation, but we don't have a PDF or anything, so we will just be using average in terms of expected value. That is minus 0.9, minus 0.8, minus 0.7, minus 0.6. So I'm adding up all these numbers and dividing by the number, which is minus 0.75. So then Y1 for S1 will be equal to minus 0.2 minus 0.2 plus 0.1 plus 0.1 divided by 4, which will be equal to minus 0.05. A little bit negative. It's not. So you see, the first one is now not equal to minus 1. It changed, it moved. And this is not equal to 0 anymore. It is minus 0.05, but it's close. And finally, Y2 for S2 is equal to 0.7 plus 0.7 plus 1.0 over 3, this kind of an averaging, which is 0.8. Okay. So these are the new outputs. Now I go back to 1. Again, the step 1. I'm iterating step 1 again. And I will run the nearest neighbor operator once again to make the new clustering, the new classification. I have now some new outputs. So which data is nearest to what? That will determine the new S1 class. So what was my data? My data was were these, okay? These numbers. So to minus 0.75, which are nearer to minus 0.75. Again, of course, the data is few, the iteration has logically started, so everything works well. This minus 0.9, 0.8, 0.7, and 0.6 in negative will be still belonging to the class represented by this one. They will be nearest to this again. So S1 will still be equal to minus 0.9, minus 0.8, minus 0.7, and minus 0.6. So it didn't change really. And S2, it will not change either. It will still be minus 0.2, minus 0.2, 0.1, and 0.1. These will be nearest to, this will be nearest to minus 0.75. This point will be, these points will be nearest to minus 0.05. And finally, S3 will be again 0.7, 0.7, and 1.0, which will be nearest to 0.8. So using this iteration, I come up with a solution which is exactly the same as the previous solution. So the classes didn't change. Since the classes didn't change, since the clusters didn't change, their centroids don't change either. I mean, the centroid of this one will still be minus 0.75. This set's centroid will be the same, and the centroid of this set will again be the same. So we stop at this point because the iteration converges. Normally, you can check the convergence of the iteration using larger data. So with 2 iterations, it's just stopped. But if you're running a computer program, or if you write a computer program for this Lloyd iteration, you may have to iterate a little bit further, because sometimes maybe the new cluster, for instance, will not include this one, and it will be included in this cluster. So their centroids or averages will also change. Yeah, that is how we perform the Lloyd iteration. We just monitor and proceed the iteration as long as these centroid figures don't change much. For example, you can put a threshold. The previous iteration was starting from -1, and now it is minus 0.75, so the difference is 0.25. You may take the absolute value of that, you may take the square of it. This 0 is changing to this one, and this 1 is changing to 0.8. So there are some errors. You take the squares of them, add them up, and monitor. And if they come smaller than some threshold that you previously designed, it may stop. At this point, it literally became 0. Then at iteration number 2, the difference between the iterated output values, decoder representation values, became 0. They didn't change. The change became 0, so you stop. And this is how you do the Lloyd Max scalar quantizer. I think in the Mergen system, I will be putting some example scalar quantizers. And for the next week, from the next week, we will continue with vector quantization, which is like we have a representation, we have an output index, which will have a representation in the form of a vector, which is a representation of other vectors. Okay, we will be doing that kind of strategy for vector quantization. And the Lloyd Max iteration will not change for the same quantizer optimization, but the concept of vector quantization is very significant, and I will probably submit my own implementation of Lloyd Max vector quantizer in the next week too. But this week I will just share the scalar quantizer, Lloyd Max scalar quantizer in MATLAB, of course. I have written a very small code for that. I hope I can find it. Sometimes I'm just losing them and I'm unable to find them. If I can find them, I will show you the Lloyd Max scalar quantizer, which you can experiment with. You may just make some random data according to a distribution, and then try to quantize and measure the quantization error by changing the number of bits that you're using. Yeah, without considering the vector quantization, there is not much else to talk about. But once we come up with the vector quantization, things will become significantly important, because it has been analytically proven that the vector quantizer itself is the optimal encoder in the lossy sense with R bits. If you have R bits for the representation of a data as an average bit rate, you don't really need to do anything further like the Huffman coding or Shannon-Fano coding, arithmetic coding, etc. If you have the optimum vector quantizer, because the optimum vector quantizer output will be uniformly distributed in terms of the indices. The index will have equal probabilities. And we know that if you have a finite alphabet with equal probabilities, you cannot compress them using lossless compression methods. So it's a little bit contradictory. It's conflicting to the concepts that we have seen before. We have seen how to compress losslessly the alphabet if they have different probability of occurrences. But the vector quantizer or even the scalar quantizer assures that the probability of these quantizer encoder outputs, the indices. By the way, what do I mean by indices? The indices are, for example, 0, 1, and 2 here. It's not y0, y1, and y2. They are just values, as you see. They are not integers. They are optimum, but their output is actually just 3 numbers, 0, 1, and 2. The encoder output is that. The decoder will take, for example, 0 as the index, and it will generate minus 0.75, which is the representation value. So anything here will be encoded as 0. Anything, any of these numbers. Any of these numbers will be encoded as 1, and any of these numbers will be encoded as 2. They will not be encoded as 0, minus 0.75, minus 0.05, or 0.8. They will not be encoded like that. They will be encoded as 0, 1, and 2. And they will be decoded or reconstructed as these. If 0 is the input, then the decoder will decode it as minus 0.75, or this or this, according to whether the input is 1 or 2. So I'm talking about these integers, 0, 1, and 2, and their probabilities will be all the same. So it will be a uniform probability distribution. And if we have uniform probability distribution, we know that it corresponds to the maximum entropy, and you cannot really compress them using Huffman coding, let's say. So although I said that the input is first transformed and then quantized and then lossless encoded, 3-stage compression, if you do one of these stages in a perfectly optimized manner, you will not be needing the optimality in the other stage. For example, if you have a perfect transformation, then you don't have to optimize the quantizer because it will be uniform, and it will not be needing any further lossless compression optimality. If the input is not transformed but given as other kind of a distribution, then the quantization optimization will work, and it will produce the indices which are uniformly distributed, so you will not be needing the lossless compression. So you will usually need these stages separately if the transform is not optimum, plus if the quantization is not optimum. For example, you don't really optimize the quantizer, but you do uniform quantization because it's easy. And many of the hardware of analog to digital converters are automatically doing a uniform quantizers quantization. Therefore, since it's not optimal, the output will have a residual probability distribution left for the lossless coder to work more efficiently. So you do standard things for the transform, you do standard for the quantization, then the lossless compression part will still be useful because some residual information is left. Some unbalance in the entropy will be left to the lossless compression side, which will be exploited at the last stage. And overall, it will be a very good compression scheme. But otherwise, if you one by one optimize these things, then you will not need the other one. You can think of it like that. Okay, so I will stop at this point. And we will continue next week, the same hour, with the vector quantization. And before that, I will try to find some illustrations, some graphical illustrations from the web, and I will also try to find my own implementation of Lloyd-Max scalar and Lloyd-Max vector quantization. So I'm stopping the recording now, and I will ask you if you have any questions. If you have any questions regarding these topics, you can ask now. If you have any questions regarding the exam, let me first stop the recording. You can ask it then. So any questions from quantization? Okay, then I'm stopping the recording.